let's get the show on the road. Good news is, it does roll pretty well by March. So, congrats to you guys. Good job. So I was going through the stuff on the AP site, looking at going over the syllabus again and again to see if we had missed anything, and I didn't miss a topic here inside of Chapter 5 that I wanted to address. That should have been done in Chapter 5, but so we're just going to do it a little bit right now. So this is just some like Chapter 5 leftovers. Let's say we ask you to do this integral here. What can we do with this? Any ideas? And how we'd go about doing this integral? Okay, so you want to factor this. Doesn't factor. Not into integer terms anyways. I don't think it has real number factors to it.
Could you just do like x to the negative 2 plus 4x to the negative 1 plus 5x to the negative 1 and take the integral of that?
So you can't break a denominator at addition and subtraction signs because you need a common denominator to make that. If it was flipped, if it was like numerator over denominator, you can break up the terms of the numerator over that common denominator, but you can't do the reverse. Right, like 1 over 2 plus 1 over 3 isn't 1 over 5, which is what you're kind of saying. You just break up the denominator. So you can't do that.
Make it all to the negative 1.
Okay, and then what's that going to do for us? That's okay, you can do that. That's a legal algebraic manipulation. But how's that going to help us do the integral? Yeah, we're at a loss, right? Paul?
Could you set the entire denominator to the
Okay, so you want to try a U substitution? This is a U substitution problem. That's why it should have belonged in Chapter 5. So if we do du dx to that, though, that's kind of a problem, right? Look at the leftovers that we have here. I don't have an x in the leftovers. I don't have a plus 4. That plus 4 is really fried my brain as to like how to even adjust that. So this is a U sub problem. This is not the correct substitution. And it's not entirely obvious on looking at this what should be the correct substitution. Here is your hint.
Sorry, I don't remember the identity. So we can.
So the antiderivative we're going to need to use to do this integral is the one for tan inverse. So somehow I need to do some algebraic manipulation to get this to look like that. Specifically, it's going to be turning this and making it look like that. this is an Algebra 2 skill. Anybody remember the Algebra 2 skill that will allow us to do that? The name of it? Starts with a C. It's 3 words. What was that? Completing the square is what we're going to be using. Very good. So remember, what completing the square does is it allows you to take some quadratic in this form and rewrite it as some quadratic in that form. Right? That process was completing the square. That ring a bell? Okay. Who remembers the first step to completing the square?
Is it negative b over, no, negative, not negative b over 2a. Just to find the third term without the variable in it is negative, is it negative b over 2a?
It's not negative b over 2. It is b over 2 squared. And now, when we had done this before, when we completed the square, we would add that to both sides, right? Do I have both sides of an equation here? What do I do then? What was, yeah, I heard somebody whispering it. Add it and then subtract it. Very good. So we'll do 4 over 2 squared and then minus 4 over 2 squared. And I'll just get the plus 5 out there at the end. Now this part is a perfect square. We can factor that. X squared plus 4x plus 4. 4 over 2 squared is 4. How does that factor? X plus 2 times x plus 2, right? Or I'll write it just as x plus 2 squared. And then I have 4 over 2 squared, or negative 4 over 2 squared, which is negative 4, plus 5 is 1. And now, this stuff matches that, right? What is the u going to be now? X plus 2, yeah. So du dx is just going to be 1, or du is going to equal dx. Oops. And then we drop our x, or resubstitute things back in. Oh, you're making some faces. What's up?
I just realized I think on my entire test I didn't put plus C.
I would have just given you 1 deduction if you did it more than once.
I told myself I was going to wrap it too.
All right. So if we look at this kind of question that I just gave you, what kind of AP exam question is this most likely going to be? A multiple choice question. So we just did a lot of work there in order to get the actual answer. Are you going to have that much time to do it, that much work? No. So let me just pull or show you what the multiple choice selections look like that came along with this. Does Mr. Kulik need to do any calculus to see the answer here? It's got to be A, because all I'm looking at is, I know that looking at the integral, that I'm going to have to use tan inverse as my antiderivative. only one answer has a tan inverse in it. That's the arctan is the same as tan inverse.
How do you know you're gonna have to use the arctan? Just because the other one has the ones. In
Because the denominator for that is 1 plus, or it's 1 over 1 plus x squared is the antiderivative for tan inverse.
Oh.
Or the antiderivative pairs with tan inverse. And that's the only way I'm going to be able to do that. I can't use sub it. I can't do any algebraic thing to it. I have to that's the tool I'm going to have to use. So if I recognize this as hey, this is completing the square tan inverse problem, all I need to do is go, oh, look, I don't even have to do this problem. And in fact, 2 of these are patently ridiculous, right?
Yeah.
These 2 are no way, right? I know that natural log inverse is a U sub problem. They didn't do any U subbing. They just stuck it in the natural log and just said, okay, that's enough. There's no chain rule. The other one is just absurd, right? We just antiderivative the bottom term by term. Can't do that. So the only one that it could possibly be are the first 2. And if I remember the antiderivative for sine, I think it's that. I know it can't be that because I don't have a square root in my denominator anywhere, right? It has to be the tangent. Don't really need to do the problem. Let's look at another, right? Before I do that, I want to point out to you guys, when we did the completing the square here, right, we did all that was kind of complicated. When Mr. Kulik sees this, because he knows he has to have a +1 left over, I would just do this as my very first step and just see if that's a perfect square, which I notice it is immediately. And I just, if I recognize this as a problem where I have to use the tan inverse antiderivative and I have to do completing the square, I don't really need the completing the square process here. I can just kind of fake it. And that makes life enormously easier as well. All right. Let me give you guys another one here. Or at least allows you to do some stuff in our head, right? Where we don't have to write a bunch of stuff down. What's the answer? Got to be E, right? It's the same form as the previous problem. If I have 1 over a quadratic, it's going to be a tan inverse problem, almost certainly. Yep.
So how do we know that let's say they have multiple arctan options for multiple choice, how do we figure out that argument inside? Is it just
It would be doing the completing the square,
okay?
right? So that is whatever is inside my completing the square.
Okay.
So if I did this, and again, I'm going to use the trick that I know that it has to have a +1 at the end. So that's the U.
Yes. Okay.
So I know that that has to be the inverse. Again, and that took me 30 seconds once I recognized what it was, without actually having to go through all the rigmarole of doing the calculus and doing the U sub. And just recognizing what was going on. And the quicker I could do that, the quicker I can logic my way to a final answer. And that's what they want you to be able to do. Right? If you have 60 minutes to do 30 multiple choice questions, they're not expecting you to do all of the problems all the way to completion by hand. They're expecting you to be able to look at the problem and go, okay, I see what's going on here. Let me look at the answers. This is the only answer it can be. Moving on. You gotta know, or you gotta be able to do that kind of thing. You know what I mean? Now, you might be concerned with the secant, right? What's the antiderivative for secant? Is that, but since the x coordinate isn't negative here, I know I'm okay. Or the x squared isn't negative. The x squared isn't negative there. I'm pretty good at that. I don't think it's going to be the secant one.
But it's secant, but isn't secant 1 over x root x squared minus 1?
Oh, is that what it is? I thought that was cosecant or something. I might be wrong. Let's go look.
Because cotangent is negative 1 over 1 times x squared.
So that's those are those. I have to. Oh boy. Oh, it's cotangent versus the negative one. Yep, you're right. So there you go. Luke was right. Good job. You really got those memorized. Yeah.
Flashcards, man.
Not messing around. Okay. What if instead we get something like this? Again, this is a problem you have all the tools to do. Thoughts?
Could you use the quadratic formula to try to factor the numerator?
Yes, you could do that. The only way that's going to help you is if x minus 2 is a factor. If you plug in positive 2, you have 72, I'm sorry, 24 minus 8 minus 25, that's not 0, so I know that x minus 2 isn't a factor of the numerator, so even if I can factor that, it's not going to help me do the integral, but good idea. There is an algebraic manipulation that we'll need to do to get this. What can I do to that thing algebraically? It's an algebra 2. Your answer lies in algebra 2. What type of function is that we're integrating? What's that thing called? You remember?
It's just the numerator or the entire thing?
The whole thing.
Oh, rational function.
A rational function, excellent. What was one of the operations we learned about rational functions?
Oh,
Polynomial division, yes. So remember,
I would just skip this one.
we'll also show you after we do it all the way through, like establish the pattern. If you can recognize the polynomial division problem, it's probably one that you can just look at the choices and pick the answer if you recognize what's going on. Okay, polynomial division. We have two ways of doing that, right? We have long division and synthetic division. Long division you can use any situation. Synthetic division is a shortcut. It's faster. It can only be used in certain situations. Can I use synthetic division in this situation? Jillian says yes. Why?
the base doesn't contain any exponents. Or the denominator doesn't contain any exponents.
Good. The denominator is degree 1, but it should also be leading coefficient of 1. But if your denominator is x to the first, leading coefficient of 1, synthetic division's a go. So let's do that. All right, so I set up my synthetic division. What goes on the outside?
2.
I set the denominator equal to 0 and solve. That gives me a 2 on the outside. Excellent. What goes on the inside?
The coefficients.
From the numerator. Excellent. Yes.
Wait, why 2?
It's the denominator set equal to 0
Oh,
solved. What do you have to be careful about when you're writing the coefficients in?
size.
And what else? If it skips a term, you have to include a 0, yeah. Like if there was no 4x there, you need a 0 in between the 6 and the negative 25. Very easy to forget that. That's why we're reminding you about it now. And if I was writing the AP exam question, I would love to include something like that. Because I'm a sneaky jerk, and that's a sneaky jerk move. All right, so we got this thing set up for synthetic division. What's the first step?
Multiply the 6 by the 2.
Not that.
Yeah, just take.
Bring down the 6. And then we do 6 times 2. And then add down. And 2 times 8 and add down. Everybody's okay with that? How does that help us?
Now it's just in the numerator.
Well, what did that allows, the synthetic division allows us to rewrite this fraction as?
Not
So what does the negative 9 mean?
but there's a remainder.
Okay. And then the 8 is
The long term.
like the constant, and the 6 is
6x.
the coefficient on the x term. So this is going to be 6x plus 8 minus 9 over the divisor. Can I do this integral? Yeah, we can. Right? So the antiderivative of 6x is 3x squared. The antiderivative of 8 is 8x. Then how do I do the antiderivative of negative 9 over x minus 2? Pull the negative 9 out front, right? And then I heard Jillian whisper, "U substitution." That's dead on. Oh, it was Paul? Sorry. It was coming from that side of the room. It was whisper, so I couldn't tell the difference between boy voice and girl voice there.
Julie. I think I'm done with this.
Feminine whispering.
No, I'm just done.
Oh. Too much trash getting thrown slung your way. My apologies. Everybody's okay with what we did there? U sub y's? So what is the antiderivative then for 1 over u? It's the natural log, that's right, of absolute value u. Very good. And then we have to plug back in for our u. Everybody's okay there? So what the pattern is, what I'm seeing, is I should be getting some kind of a polynomial, and then I'm going to get the natural log of some of the divisor. Everybody's okay with that? That's the pattern that I'm looking for. So if I look at the actual full multiple choice problem, and I look at the answers, only 2 of them are plausible right away, right? Those 2 are gonzos because they don't have a natural log of x minus 2 in it. And now if I look at the other ones, why should I be able to immediately discard C? There's a couple of reasons you could give.
The cube.
That's too big, right? Because I know x squared divided by x to the first should be x to the first. So if I integrate it, the biggest power should be x squared. So immediately I could discard it because of the cubed. Excellent. Everybody's cool with that reasoning? Another is because I know the natural log should only be multiplied to the remainder of that synthetic division. Here it's multiplied to the entire quotient. I know that's bad juju also. Either reasoning, that one's gone, has to be A. Again, and I did potentially no calculus to get that. I just recognized this is a synthetic division problem. My answer has got to have a natural log in it. Which one of these is a plausible answer? No calculus done. This could be a 1-minute problem. And it needs, like, these are the kind of the problems that need to be 1-minute problems because you'll run into other stuff that just aren't 1-minute problems in there. You know, where you have to be able to make them some time. Elsewhere, this is an example of a kind of a problem you can make them some time. Let's look at this one and see if we can do this without doing any calculus. Now this one's a little harder. What makes this harder? It's a definite integral, right? Ugh. Which are the 2 that you consider right off the bat? A and C, right? So those are the only, let's cross out those ones. I agree. All right. So how am I going to tell the difference? Well, I know that I'm going to have stuff plus, you know, like a constant times the natural log of x plus 2. And then I'm going to do that from 2 to 1, right? So I'm going to end up with the natural log of 4 minus the natural log of 3.
Wait, how did you do that? Oh,
Because I plugged the 2 in for x to get 4, and the 2 in for 3 to get, or 2 in for x to get, or the 1 then in for x to get 3. Right? When I do the definite integral, I'm going to have stuff evaluated at 2, natural log evaluated at 2, minus stuff evaluated at 1, natural log evaluated at 1. So I know I'm going to have this somewhere, which is just the natural log of 4/3 using my limit or my log rules. So I like that one. Again, didn't have enough time to do the whole problem. But if I know what I'm looking for, like what the answer has to look like, there's places to trim some time. It's kind of what we're showing you how to do here.
can you explain how you're going to have like log minus, or natural log minus natural log in that?
Well, it's going to be like stuff evaluated at 2 plus that, and then I'll have minus stuff evaluated at 1 plus, right? When I'm doing the definite integral, I take my answer and I evaluate it at 2 and then minus it evaluated at 1.
Right, yes.
So when I plug the 2 in for x plus 2, I have 4. When I plug the 1 in for x plus 2, I get 3. And I distribute my negative sign through. And I'm going to have
How would you know the format was like stuff evaluated as something plus natural log of that?
Well, that's what we just talked about, was that when we did our answer, you're going to get like the antiderivative of the quotient, plus or minus the remainder times the natural log of the divisor.
Oh, okay.
So I'm just kind of
Yes,
using
now
that
I
pattern,
see.
like
Yeah,
every
okay.
synthetic or every polynomial division problem is going to kind of follow that pattern.
Okay.
That's what I'm taking advantage of. Is I'm just like, okay, I know that I have to have that stuff, whatever, plus a natural log of the denominator. That part I know with just looking at the problem format. I don't have to do any calculus to know that, because I've done these problems before and I see it. It's like, okay, polynomial division problem, because I checked to see if I could do something easy, like just factor and reduce. I couldn't. So that's what I'm getting at. Does that feel okay?
Yeah.
Let's do a tricky one here. And this is an example of one where I think that I would have to do the whole thing to get this right. Now, right away, I can do one thing. Cross out A. But I don't think, without doing a little bit of investigating, I'm going to get the right answer without really kind of pouring through this. Now, I recognize that from looking at it with the square root and the x squared being negative, that it's going to be a sine inverse problem. But I have 3 sine inverse choices. So that doesn't help me a whole lot. So I'm going to just start by doing my completing the square here. Okay with that? So what I'm really going to be, because I know that I have to have 1 minus x squared there. I know that I have to, keep that negative sign. Okay. So I'm going to have 4x plus 4, and then minus 4. And then I'm just going to boot the square root, or the negative 12 out. But in doing that, I'm going to kind of distribute the negative sign to it. That's why it's a plus 12. And then I'm going to boot out also the negative 4. So I have that. Or just there. And now I go, oh, okay. What's the problem with what I have? To be able to use that antiderivative, I should have a 1 there. What do I have? 16. How do I solve that? How do I remedy that problem? factor a 16 out of all of that. Now when I factor a 16 out of that, that's the same thing as dividing by 16, or really multiplying by, write it this way, I'm sick of doing this, 1 over 16. Everybody's okay there? Okay. And what do you notice about 16? It's a perfect square, right? So I can think about this as like 4 squared. So I can absorb that now inside of my quantity there. That allows me to get rid of option C, because I know it has to be x plus 2. Yay! That's something. What's the difference between B and C? The coefficient, right? And at this point, I'm not sure which one is going to be the one I want. So we're just going to kind of keep going on this. So let's get back to where we are. So I'm going to put this all back into the problem. Oops, and this was all under square root. So I'm going to pull the square root of 1 over the square root of 16 out front. Or just write it as 1/4. I guess we've got to do our u sub. So du dx is going to be 1/4. So 4 du is going to equal dx then, right? Shoot. That's not right. We goobered something here, guys. Give me 1 second to go back through. I lost the factor of 2 somewhere along the lines. I multiplied 4 to both sides, right? Where did we go wrong?
Wasn't there an 8 originally?
Oh my gosh, yes! Thank you! Luke with the save. So the problem originally had an 8 in the numerator. So that can just come all the way with us to the end. Yes, thank you, sir. I was going crazy with like, what the heck did I do? It had to have been something simple. But that was one where I don't know that if I could have sat there and thought about it for a while, and I don't think I would have been able to figure out which one of those two was going to be without actually like running through the procedure there. That one's just kind of like a dead end time suck. But to be honest with you, if I got to this point here, where I knew it was a 50-50 between those two, I might have just, after a minute or two, might have just cut my losses and guessed. Because remember, what does a 50% on the AP exam look like? It's like a 4. If I can turn every multiple choice into a 50-50 problem, I'm doing great. I'm feeling great about myself. Okay? 50% is 4. It's 4.
You would be the least people.
If I can turn every multiple choice question into a 50-50, I like my odds. I'll just worry about doing well in the free response stuff, and I'm going to guess that probably along the way there's going to be multiple choice ones that after a minute or two I absolutely know. But I feel pretty good. Paul?
If you zoom into the answers, I notice a trick is that like they like to try to just prey on the factor to get one part wrong. So like the 8 being the coefficient in front of 2 problems opposed to the 2, like I would think there's a higher chance that it would be the 8 side opposed to the 2 side. If that makes sense.
Okay. I think you're trying. I think trying to psychoanalyze the AP exams is
I don't know.
rough. That's not a game I would want to play
Okay.
with. But
If you're gonna, I'm just saying if you're gonna make the 50-50.
if you're gonna 50-50 guess it,
That's it's not like you shouldn't go into the test thinking I'm gonna analyze really
Yeah.
hard, but
sure.
I've had testing success with that.
Okay. Fair. If you're just down to like it's 50-50 between these two, I just need a reason to pick one versus the other. That's as good a reason as any. You know. All right. You guys feel okay on kind of what we did here? Again, it was nothing. You did nothing here today, or in this little section that you didn't using techniques you didn't know already. All right. On to chapter 6. So, chapter 6, we're going to look at areas between curves. So, our goal would be to figure out, like, okay, what's the area for that region S? Right, that's the area between those two curves. So, what I'm going to do is I'm basically going to build a bunch of rectangles to approximate that area, right? So like the rectangle I build looks like that. I'll call the base of that rectangle delta x. And the height of that rectangle then is going to equal this y coordinate minus that y coordinate. Everybody's okay with that? And then if I take an infinite number of those rectangles and add up their areas, that should be S, right? Everybody buy that? Okay.
So you f of x minus g does the okay no that makes sense.
So again, if g of x is below the y-axis, that's a negative y coordinate. So when I minus the negative, it adds it to the height.
Okay, that's all.
And notice that this is going to be equivalent to just saying, okay, I'm going to take this area that's above and this area that's below and just subtract those two areas, right? Area above minus area below. By minusing the negative area below, it makes it positive. It's the same idea. So this, we can then just turn into our formula for integration. It's just the integral from a to b, where a and b are the intersections of the two functions, more than likely. What happens, what does this formula become if g of x is 0? If g of x is just the y-axis, or the x-axis? The integral of f of x, right? Which should make sense, because that's the area between f of x and the x-axis. Cool. I like it when my new formula generalizes into my old formula, or is just a generalization of my old formula, right? Okay. It's some example time. So here we're asked to find the area of the region bounded above by the curve y equals e to the x, and bounded below by the curve y equals x, and then bounded on the sides by x equals 0 and x equals 1. So I've gone ahead and included a picture of that region. Everybody's happy with that? So we're going to be integrating from 0 to 1. And the heights of my rectangles are going to be e to the x minus x. And the widths of my rectangles are dx. Everybody's cool? What's the antiderivative of e to the x? The antiderivative of x. And we evaluate from 0 to 1, we have e to the first minus a half, and then we have minus e to the 0 minus 0. So that turns into just e minus 3 over 2. What do we notice here? This integral was real easy, right? That is typically going to be the case, that the integration will not be terribly challenging. The setup is usually the hardest part. In fact, really the hardest part is getting your picture drawn accurately so that you can figure out what to do.
Where did the 3 over 2 come
E to the first, or e to the 0 is 1.
from? Okay.
So 1/2 minus, or negative 1/2 minus 1 is negative 3 over 2. Let's do another example. We're going to find the area of the region enclosed by the parabolas x squared and 2x minus x squared. Notice what's not given to me in the words. The a and b, the bounds for my integral. Very good. So if we look at the picture, the bounds are clearly labeled, right? What are the bounds in the picture? 0 and 1, right? How would we find those if they weren't given in the picture? Set them equal to each other. Very good. So then I can just solve algebraically, right? Factor out at 2x. Everybody feel happy with what we did to find the bounds?
Yeah.
All right, so we have that. So then we're just going to do the top, which is 2x minus x squared, minus the bottom, which is x squared, dx. I'm going to simplify that a little bit, because x squared minus x squared is just minus 2x squared. And I guess I will probably pull a 2 out of that out front just to make life just a little teeny bit simpler. The antiderivative of x is x squared over 2. The antiderivative of x squared is x cubed over 3. And then we're just evaluating from 0 to 1. So we have 2 times 1/2 minus 1/3 minus 0 minus 0. So that's 3/6 minus 2/6, which is 1/6 times 2, which is 1/3. Okay.
Why does the x squared become negative? Sorry. The y equals x squared, why does it become negative?
Because it's f of x minus g of x.
Oh,
So just the formula, right?
yeah, sorry, I used x squared as my f of x.
Ah, yep. So the top has to be f of x.
Oh, and,
Right.
Okay, yeah.
So like the top of our function here is f of x, and the bottom is g of x.
Oh, okay. Thank you.
Yep.
What was your answer?
1/3. Okay. Here it says find the approximate area of the region bounded by the curves y equals x over square root of x squared plus 1 and y equals 1/4 minus x. What word in the directions is different than the previous problems? Approximate. Why do you suppose that that's included?
They don't define the bound.
We're not given the bounds. Can you algebraically solve x to the 4th minus x equals x over the square root of x squared plus 1? I don't know that I could.
Oh, really? It's like hard.
Oh, yes. You're going to have like a massive degree polynomial. Yeah.
Wait, you don't know how to?
I mean, I'd have an idea, but I think it's going to be very ugly, and I don't know that I could do it without a calculator because I suspect the polynomial that you'll end up solving will have no integer valued roots, no rational roots, and I'm not really sure what to do with it once I got that far.
Oh, yeah, okay, it's way like scary.
Yeah, it is way scary.
Yeah, I liked it. I said yes. I was like, oh, it's just
Yeah, you do.
That's
You do. And then you'd have to like
actually
square both sides and
That's
then clear the fraction,
Yeah.
and it gets like, you end up with like a degree 10 polynomial
That's
or something. And that seems like a problem to me. All right, so what are we going to do instead? Yeah, I'm going to use my calculator in the intersect command. You got it. I think I remember that was yes.
Like, can I just, like, because that kind of looks like 1.3, let's say. Yeah, sure. Wait, yeah, 1.3. Can I just, like, say that's going to be 0 to 1.3?
Well, it would probably give you a within like to 3 decimal places or something to like keep you from being able to do that. So I'll go ahead and just set them equal to each other. Looking at my graph here that I was given, I'll use that to set my window. So -1 to 2 and then -1 to 1.5. Seems good to me. So there's the top and here's the bottom. Now this one, like I can clearly see that if I put 0 in for x, I get 0 equals 0. So like that was I can do that without my calculator. To get the other intersection, though, is going to be a problem. So intersect command.
So we're just looking where the intersect.
Yes. Now my calculator So here I'm going to be a little bit careful since there's more than one intersection. First curve, second curve, and then I'm going to move like real close right on top of it, do my guess, just so it doesn't accidentally find 0 and I have to redo it. So I got about 1.81 or 1.181. Excuse me. What do you think now?
It's like not fun. Like, do it.
It's not so bad. So we're just going to separate. Yep. So the first one's a classic U-supper. So what should our U be in that first one? And then so du is going to be, d over 2 is going to equal x dx. So I'm going to have 1 over, well, let's write it this way. Let's write it u to the negative 1/2 du, and I have that over 2. And I have x to the 5th over 5, and x squared over 2. So what's the antiderivative of u to the negative 1/2?
Wait, what?
Yep. So 2u to the 1/2. Now, what do I have to be careful about here? I have to put the x squared plus 1 back in for my u. Excellent. Because I didn't bother to change my bounds, because the rest of the integral was just in terms of x's. It felt like it was just going to be easier to put the x back in. And this is now something I would type into my calculator, because I don't want any part of trying to do that by hand either.
If you changed your bounds, could you even?
Oh, why don't I even just do this? I'm going to just do it in my calculator.
Oh, Mr. Cooley, if you changed the bounds of your u, would you only evaluate that?
You would only do it for the u sub 1. The other ones would stay the same.
Normal one, right?
Yeah. Yep. Which is another reason why I didn't bother to do it, because it just felt like that was going to get confusing. All right, you stupid machine. I just created you. Not in my usual setup. Computers being very difficult. Hi.
I don't mean to interrupt. I just wonder where you are today for community time.
8-5.
8-5. Okay.
I think it's also pasted on my door.
Oh, all right.
The where to go today.
So I didn't have to interrupt your class and cause a big disruption. How's calc going, guys? Awesome. The best class you've ever taken?
Yes.
Heck yeah, it is. I
Oh,
don't have
what's
any detentions to give any of you. This is ridiculous.
So you're okay with us using like the definite integral on our calculator now that like we're kind of past that test? Like,
Here's what I would say.
I'm doing the homework. There's like a lot of that where it's like I don't want to hand
Like,
write it out.
once you've gotten to this point, like you've done the antiderivatives by hand,
Okay.
I would not do the plug-in by hand. I would just go back and do the original problem on my calculator and write down the decimal. because I'm more positive that that part
He
is.
wants to get to kind of that part before we.
Yeah.
That's fair.
And again, like as we get deeper in, there'll be stuff where it's just like set up, show me the setup, and then use your calculator. And there'll be stuff like do this basically without your calculator, meaning like show me the work. You can still use your calculator to like check stuff or whatever, but like, to show the work to do it. Because some of the stuff will be like, quite frankly, in a test setting, unrealistic to do everything by hand the whole way through. It'll be like, hey, show me the integral that you're doing, and then do it on your calculator. Set up the integral, do it on your calculator. That's fine. And there'll be problems where it's like, do it all, but it won't be every problem do it all. You know what I'm saying? Jim.
Sorry, can I see your calculator one more time?
Yeah.
Just 1 second. Should that be x to the fourth minus x or minus? Minus again. I did it again.
Distributed the
Yeah,
minus,
I
so
did
it's
it
minus a
again.
negative, which is why I wrote it as positive, just to save myself the parentheses.
Yeah,
Yep.
I did it again. Okay, sorry.
No, it's okay. It's okay. If you didn't get the right answer,
Makes sense.
we need to know. What if we have something like this, where the two curves switch who's on top and who's on bottom over the course of our interval? Well, let's say that those spots are C and D. We'll just go A to C, and then we'll do f of x minus g of x dx. And then where they switched, we'll go from C to D, and then we'll have g of x minus f of x dx. And then where they switch back, D to B, we'll switch back to f of x minus g of x dx. Right, so just break up the problem into several integrals based on who's on top and who's on bottom. Which hopefully was like the obvious thing that you would have come to doing, right? Because we need to make sure that they're positive. What is this the same as? The absolute value of the difference. Now, do we have an antiderivative for an absolute value? No. What did we do every time we had to integrate an absolute value? We did that, broke it up to like, where's it above and below the x-axis? So it's the same. Everybody's okay with that idea? But this is really the way to think about it. It's just breaking it up and changing the formula for who's on top and who's on bottom. All right. Let's do this one. I want to find the area of the region bounded by the curves y equals sine x and then y equals cosine x on the interval from 0 to pi over 2. So I've included the picture. Let's pretend we didn't have any picture and we don't have a calculator. Well, cosine of 0 is 1. Sine of 0 is 0. So cosine starts on top.
And you use 0 because it's like easy.
I used it because we're going from 0 to pi over 2. Okay. And then let's see at the, so this is at the beginning. Let's see what's going on at the end. So cosine of pi over 2 is, and sine of pi over 2 is 1. So at the end, sine is on top, and cosine is on bottom. So at some point they switched, right? How do I solve that? Okay, you might be able to get it by inspection that it's pi over 4. That's true.
Well, it's like the values for cosine and sine when it's pi over 4, they both can be square root.
Yeah. No. You're dead on. Dead on. You can do it by inspection if you have it memorized. You can divide both sides by cosine also. Sine over cosine is tangent. Tangent is equal to 1 at pi over 4. You can do it that way as well. So either way is fine, whether you've memorized your unit circle well enough to where, like, on site you're like, okay, those two are equal at pi over 4. Or you might have to do it algebraically a little bit. So we're going to go 0 to pi over 4. And then we'll have cosine on top minus sine on bottom. And then from pi over 4 to 1, or to pi over 2, excuse me, we have sine on top and cosine on bottom.
So why did we choose one? Pi over 4?
It wasn't choose, we found.
Yeah, how? Why?
Well, we need to figure out when they switched, right? Because we noticed at the start, one was on top, or cosine was on top, sine was on bottom. At the end, sine was on top and cosine was on bottom. At some point along the way, they switched. We had to figure out where that happened. So we set those two equal to each other and solved.
Okay.
That's how we got pi over 4. That's where they switched at.
Because when tan is equal to 1 and x is equal to 5.
Yes, or you could have done it by inspection and remembered that the place where sine and cosine are equal is at pi over 4.
Okay.
They both have root 2 over 2 on the unit circle. You could have remembered that from your unit circle also. That would have been okay as well. It's 6 of one, half dozen of the other. Okay. So, antiderivative of cosine is sine. Antiderivative of negative sine is cosine. Antiderivative of sine is negative cosine. Antiderivative of negative cosine is negative sine. Okay. So sine of pi over 4 and cosine of pi over 4 are both root 2 over 2. And then minus sine of 0, which is 0, and minus cosine of 0, which is 1. Then cosine of pi over 2 is 0. Sine of pi over 2 is 1. And then we have cosine of root 2 over 2 and sine of root 2 over 2. Oops. Minus in there. So I have, let's see, we have 1, 2, 3, 4 over 2, so that's 2 root 2's, and then minus 2. Okay. All right. Paul. Absolutely. Last idea. What happens if we have something where our functions are written in terms of y rather than x. So instead of y equals yada yada yada, we have x equals yada yada yada. Does that change the fundamental ideas here? No. Right? Because we know that fundamentally integrating and we change the name of the variable doesn't change the value of the integral, right? What it will do, though, is affect the setup a little bit, because instead of looking at top versus bottom, we're going to look at right minus left. But that's the only difference. So, let's look at an example. Find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Notice here I didn't give you any picture because I want us to do the picture by hand. Because this is not one that you can type into your calculator because the y squared. Or at least one you can easily type in your calculator. So let's start here. How many points do we need to graph the line y equals x minus 1? 2. So what are an example of 0, negative 1, and 1, 0? What's the smallest output that y squared can have? 0. What value of x is going to give me a y value of 0? Negative 3. That's basically like my vertex of my parabola. And then I'm just going to pick some values of x's, and I'm going to settle on whenever I get an integer value here for y, right? So if x is 1, y squared is 8. 8's not a perfect square, I don't want to use that one. If x is 2, y squared is 10. Don't like that. If x is 3, y squared is 6. Don't like that. If x is 4, y squared is 14. Don't like that. If x is 5, y squared is 16. Yeah, I like that. So I'm going to have 5, 4, and then 5, negative 4. And again, you could have used those other values of x that I discarded. You just would have had decimals, which would be fine, but like, yuck, I don't want them. So let's draw this one maybe in orange.
Good morning, Notre Dame Prep. Please excuse this interruption. At this time, I would like all freshmen to make their way down to the gymnasium. Freshmen, you're going to make your way down to the gymnasium. We're going to leave our backpacks on the gymnasium floor. Thank you, and God bless.
I'll do this one in blue. So I have negative 3, 0. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. All right, and we're looking then for like this region in here. Everybody agree? All right, let's find those points of intersection. How do I do that? So what I think I'm going to do is I'm going to substitute this in for y squared. Just seems relatively easy way of doing that. So x squared minus 4x minus 5. That factors to x minus 5, x plus 1. So here we have negative 1 something, and this would be positive 5 something. Well, that one I know is 5, 4. And then negative 1 for x should be negative 2 for y if I plug back in here. Everybody's okay with that? Now, with which variable do I want to integrate? X or y? Y. Notice if I try to do x's, which curve is on bottom? Over here, it'd be the yellow, but I don't want to integrate all of this stuff, right? It would be a more difficult integral to set up correctly to integrate with respect to x. If we integrate with respect to y, I can do this all in one shot. So my function on the left is going to be this one. But what do I have to do to that? I have to rewrite it so that it's in terms of y. And similarly here, that's my function on the left. I have to rewrite that so it's in terms of y. So I'll subtract 6 and then divide by 2. And then it's just like any other integration problem. We've done a bunch of these. Let's see. If I simplify this down, I'm going to end up with minus 1/2 y squared. That becomes plus 3, so plus 4 dy. And so we got y squared over 2 minus y to the 3rd over 6 plus 4y negative 1 to 5. Oops. Oops, 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 oops. What did I do wrong? Why am I saying oops a bunch of times? Yeah. Yeah, it should be y coordinates there. Dum dum. I know, me too. And then I'm going to let you guys plug in from there. I think we're out of time. But that's pretty good timing, right? So the homework for 6-1 is here. We're going to go back, or next time we'll do 6-2. First hour is going to take a day of extra practice on 6-2 to let us catch up, because they're a day ahead because of the snow day still. So that's going to be the plan. And then we'll all be on sequence then on Friday for 6-3. Just FYI, 6-2 and 6-3 was challenging sections of this chapter. So be ready.